Now that we've introduced System Verilog, we're ready to start designing a large-scale digital logic design. What should we design? Well, a CPU, of course. In previous instances of this course, we designed a MIPS CPU because this is the architecture with which you are familiar from CSCE 212. This semester, we decided to switch to the more modern RISC-V CPU architecture, which is very similar to MIPS and actually simpler in many ways. RISC-V was designed as a free instruction set architecture as opposed to MIPS and ARM, which are licensed. RISC-V also addresses some of the odd and difficult to explain aspects of MIPS. Hopefully you remember that the native language of a CPU's hardware that is accessible to the programmer and forms the interface between the software and the hardware is called the instruction set architecture. So instruction set architecture is really sort of equivalent to saying the assembly language, and also the way in which the assembly language is translated into the machine instructions, the binary form, machine language. But the logic circuits that execute the language under the hood, that's called the microarchitecture. So there's instruction set architecture, which is the interface for the programmer, and the microarchitecture, which is the underlying implementation of the processor. Instruction set architecture, as I mentioned, includes the assembly language, which is the textual form, and the machine language, which is the binary form. Each instruction set architecture has its own specific assembly language. There's a huge number of instruction set architectures. So Intel, Spark, Alpha, MIPS, ARM, RISC-V, VAX, IBM 360, Convex, Cray, C66 digital signal processors, AVR, the ZIP CPU, the Commodore 64, and the NVIDIA PTX are among the set of instruction set architectures that are out there, and they all use different assembly languages. But once you learn one assembly language, it's generally very trivial to learn any others. An assembly language program is comprised of a repertoire of primitive operations that are called instructions, each identified by a mnemonic, which is an abbreviated single word that names the instruction and appears before its operands in the assembly language program. Each instruction can perform a single, simple, primitive operation, such as to add two values, compare two values, or select the location of the next instruction that's executed after the current instruction, which would be a branch or a jump instruction. Numerical and logical operations can only be performed on values that are in the CPU's register file. And since the register file is small, values must first be brought into the register file from an external memory or from an I/O device using a load instruction, and all of the computed results must be transferred from the register file back to an external memory or an I/O device using store instructions or a store instruction. Just like MIPS, RISC has 32 general purpose registers, with register 0 always containing the value 0. Also like MIPS, registers 1 to 31 are designated for special uses according to a convention. But in this course, since we're only writing simple programs and we're not linking our code with code written by anyone else, so you're writing all the code, we don't need to follow these conventions. Recall that MIPS addresses registers in the assembly code using a $ prefix, such as $2, while RISC-V uses the X as a prefix, so you would use X2. RISC-V specifies standardized subsets of its instructions. In this course, we will be implementing most, but not all, of the RV32I, which are the integer instructions, and the RV32M instructions, which include the multiplies, instruction groups, subsets. So those are the two sets of instructions we are targeting in this course for our projects. Most of these instructions use the R, I, and B encoding formats. But there's also the S-type, J-type, and U-type encoding formats that are weird corner cases designed for one-off or specific instructions. So S-type is for stores, J-type for jump and link, and U-type for load upper immediate. Of the instructions we will implement this semester, the ones I'm showing here all behave in a similar way in that they all read two source register values. They perform an operation as indicated by the instruction's mnemonic, and then they store the result back to the destination register, which is the register listed first in the assembly language version of the instruction. Operators in this list that have a S or a U subscript represent the signed or unsigned version of that operator. For example, a signed less than operator would consider the leftmost bit of each of the operands as the signed bit, while the unsigned version of the set less than operation would consider the leftmost bit to carry a value of 2,147,483,648, which is 2 to the 31st power. Now, the instructions I'm showing here are similar to the ones I just showed, but the difference is that they include an immediate value or a literal constant as serving as the second operand of the instruction. The instructions I'm showing here are different in that they are change of control instructions. They essentially prevent the CPU from executing the next instruction in the program and instead cause it to begin executing instructions at another memory location as defined by the branch or jump target. Then we have load and store instructions. We're just going to implement one load, the load word, and one store, the store word. Then we have instructions that read or write I/O registers. In this course, the I/O registers will comprise the CPU's interface to the switches, keys, LEDs, and hex displays of the virtual DE2-115. So this will allow your CPU to get inputs from the user and output to the displays on the virtual DE2. You might remember the following strange things about MIPS from CSCE 212. MIPS treats immediate values differently depending on the instruction in which you use them. MIPS will sign extend the immediate in the add I instruction, but will zero extend the immediate in the AND I instruction. RISC-V, on the other hand, just sign extends all immediates, regardless of the instruction. In previous iterations of this course, we needed to add an extra control signal and a mux to support both the signed and zero extended immediates, but now with RISC-V, we don't need that anymore. MIPS has signed and unsigned variants of the add and subtract instructions, the difference being whether or not the CPU will trap on an overflow resulting from the signed version of the instruction and ignores overflow on the unsigned version. RISC-V only has one variant of the add and subtract instruction and doesn't support trapping on overflow at all. MIPS has a special high and low register that it only uses for multiply and divide. RISC-V doesn't do this. Compared to MIPS, not having high and low reduces the size, the number of inputs of the mux that routes data into the register file. MIPS used the RD field in instruction bits 15 down to 11 as the output register for R-type instructions, but used the RT field in instruction bits 20 down to 16 as the destination in I-type instructions. This necessitated an extra multiplexer in the critical path in the write back stage. RISC-V only uses one destination field, the RD field, which is in instruction bits 11 down to 7 for all instructions that write to a register, so no need to have the register destination mux. MIPS had a weird J-type instruction that allowed for pseudo-direct addressing for jump targets. I was hoping RISC-V would have done away with this, but it didn't. It still has a J-type format that is only used for jumps. It's only used for one instruction, whole format for one instruction. But it uses a PC relative address, much like the branches do, which is a bit more sensible. So the difference then between the jump instruction and a branch is that there are extra bits allocated in the J-type field for the offset, so you can jump farther away. MIPS also did this strange thing where it used the contents of the second register source, the RT field, as the value to be shifted for shift instructions. So what that meant was on your ALU, whenever you had a shift, you would actually be shifting the B input, the secondary operand input, instead of the first operand input. That never made sense to me, but we had to deal with it with MIPS. Luckily, RISC-V uses the first operand for shifts, which makes a lot more sense. The MIPS assembler, at least all the ones I used, always uses register 1 as a temporary value when expanding pseudo instructions. So for example, if you use a load or a store and you used a symbolic target, then it would use register 1 to load the base register for the load and store. And sometimes this caused errors if the programmer was using register 1 before the pseudo instruction was expanded in the code. But RISC-V allows the programmer to explicitly provide the temporary register value, although to be fair, this is something implemented in the assembler instead of the hardware, but it's still, I believe, written into the RISC-V instruction set. I think the best way to illustrate how these instructions work and how to use them is to write a program. Learn by example. So let's write a program that computes permutations of n unique values with the permutation length of L. And L can be 1 to 6, and I'll explain why we have that limitation in a minute. For example, for a length 3 permutation of 4 values that are labeled 0 to 3, we would have 4 factorial divided by 4 minus 1 factorial, or 24 permutations shown here. Think of each of these values as having 3 slots. So the length represents the number of slots, and each of the slots are populated with a 0, 1, 2, or 3, and you can only have one instance of each value at a time. So again, there are 3 slots. Each slot has a value from 0 to 3. You can only have one value per permutation. An easy method for computing these values, these permutations, is to perform a depth-first search, which is a very simple algorithm that relies on having access to a stack data structure, as well as a function that can expand a partially completed permutation into a set of partial but more complete or complete permutations. So in other words, the expansion can take a partially completed permutation, which is partial because some of the slots are populated and other ones are not, and it can expand this into a set of more complete or possibly fully complete permutations. Initially, an empty state is pushed onto the stack, which in this case is empty, just has L empty slots. The algorithm will repeatedly pop a value from the stack until it is empty, and if the popped value is a complete permutation, it will just print it out. And if the popped value is a partial permutation, it will expand the permutation and into a set, and we'll push each one of those back onto the stack, and then repeat the process. The expansion function locates, the way that I will write it, it will locate the furthest empty slot to the right, least significant, and attempt to populate it with each of the n possible values. Of course, it will only be able to actually populate it with the values that haven't already been used in other slots, slots to the right that have already been populated. So for example, if we pop the value xx2 from the stack, where the x's indicate the empty slot, so xx2 is 2 empty slots followed by a 2, then we would expand that and push the values x02, x12, and x32, and push each of those back on the stack. In our program, to simplify things, our permutations will be 32-bit values, or 8 hex digits. Each slot will comprise 4 bits, or 1 hex digit. And we'll use the leftmost 8 bits, or 2 hex digits, as a bit vector that represents which values have already been slotted in the value. Okay, so for example, the hex value 06FFFF12 indicates that the rightmost slots contain the values 2 and 1, reading from the right to the left, and the leftmost byte contains the value 6, which is a binary value 110, which indicates a 1 in bit position 2 and 1, which corresponds to the fact that we've used values 2 and 1 in that partial permutation. Now notice that there are 4 F's in there, which means that we have 6 empty values. We may only be planning to construct permutations that say have 4 values, for instance, in which case, the first 2 F's on the left will never be populated, right? They're just, but this gives us a limit of 6 total slots in our permutation. Of course, we don't need to use them all, but we have a maximum of 6 because we're using a 32-bit word to represent these permutations. Now, this program is too complex to write directly in assembly language, trust me. So we'll write a C version first and then convert it to assembly language. And in addition to providing a template for the assembly program, we can use the C version as a point of comparison when we're debugging our assembly code. I found that this is very helpful. You might think it's too much extra work having to write basically 2 versions of the program in 2 different languages, but it greatly simplifies the debugging process, and I say that from experience. Okay, so let's write this program. I have my virtual machine up. I will begin by making a directory for my code. I'll call it permutation. I'll go inside there. I'm going to use Vim to create my source code file. I will call the source code file permutation.c. And I will begin by setting some things up, setting up my tabs. Okay, the first thing I'm going to put in this file is I'm going to say include standardio.h so I can use printf, and then I'm going to define the 2 parameters that I discussed earlier, which would be L, which is the length of the permutation. I'll set that to 3, and N, which is the number of values in the permutation. I'll set that to 3. So this will give me 3 factorial permutations. It'll give me 6. Then I'll start my main function. And inside there, I will allocate some space for a stack. And I will declare and initialize my stack top. But then I'm going to go ahead and just push my initial value to the stack, which will be 8 bits of 0, which represents the bit vector, meaning that no values have been set inside there yet, and then that will be followed by 6 empty slots denoted by hex digit F. So it's 1, 2, 3, 4, 5, 6. So obviously the maximum L value I can use is 6, and the maximum N value I can use is 8, because I have 8 bits in the most significant byte that I'm using to denote whether I used a value, and then I have space for 6 empty slots. So we will begin with our main while loop here, which will keep iterating while there is data in the stack, meaning that the top is non-zero, and then I will begin by popping. I'll pop a value off the stack, like so, and I'm also going to declare a flag called found that will be set to 1 if the value that I popped can be expanded. If it can't be expanded, then it is a completed permutation, a terminal value, and I can print it. So the first thing I need to do is I need a loop that will scan the slots from right to left to find an empty slot, an F slot. So for, let's see, int, let's see, I'll call this digit equals 0 as long as digit is less than L, which is the number of slots, the length, digit plus plus, and inside here I need a way to check to see if the slot is empty. If the slot is empty, there'll be an F in there, so I'll create a mask which will be set to F, which designates an empty slot, but then I need to shift it by digit times 4 to put that mask into the position of the digit or the slot that I'm interested in. The shift operation is in terms of bits, so I have to multiply by 4 because each slot is 4 bits. And then if I take, let's see, if I take the value and I mask it and it with the mask, if that value equals mask, that means that all 4 bits in the bit positions denoted by the mask are set to 1, meaning that I have an empty slot. In other words, those 4 bits are all 1s. So that's going to denote an empty slot. If that's the case, then I can set found to 1, meaning that I've found an empty slot, and thus I can expand this permutation. And then I need another for loop that will run through all the possible values that I can put in that slot. So for I equals 0, I less than, in this case, n, because n is the number of values that I can choose from. I'm going to run through all of those, but I first need to check to see if that value's already been used. So I'll say if it is not the case that val anded with a 1 shifted to the left by 24 plus I. Okay, so I'm taking a 1 and I'm shifting it 24 bits so I can get it into the most significant byte where my bit vector is. Then I'm adding I to that, which will put it into the position of the value that I'm interested in. And also I'm going to put parentheses around the shift amount. Yeah, 24 plus I should, sorry about that. 24 plus I should be the bit position in the most significant bit that the most significant byte rather that corresponds to the flag that corresponds to whether or not I've used that corresponding value. Sorry. So if that is not the case, then that means the value hasn't been used yet. So I will go ahead and expand. So during the expansion, I'll create a new value from the old that will be the old value. And the first thing I'll do is I'll take a 1 shifted by 24 plus I, and this will again set the, instead of in the if statement I was checking to see if this bit were 1, but now that it was 0, now I'm going to set it to 1. And then I will have to 0 out the slot. So it will be, I'll have to take new val and I'll have to and that with the complement of mask. So the complement of mask will be all 1s except for 0s in the position where I originally had 1s for the mask. So there'll be a set of 4 zeros that line up with the slot that I'm filling. That will be zeros, so I'll end that with new val, and that will zero out the empty slot, and then I can do an OR with the value that I want to add, which is I shifted by 4 times digit bits to the left. So again, the first line of code here is setting the bit saying that I've used this value in this partial permutation, and the second line is actually inserting the value into the appropriate slot. And then once I do that, then I can just push that value onto the stack. All right, so let's see. If I get through the whole for loop, that means that I have done all my expansion. And if I got into that for loop at all, it means that this if statement here was true, meaning that I found an empty slot. So I only want to expand one slot at a time. So I'll break, which will break me out of this for loop that's going through all the digits, all the slots. I don't want to expand more than one slot at a time. And then once I have finished looking for empty slots, if I never did find one, that means that my value is a terminal value, is a completed permutation. So this would be indicated by found never having been set to 1. So if found is 0, then I'll print out the result. So this will be, let's see, I'll do some formatting here, 06x, so I'm going to print this as a hex value, which makes sense because each hex digit is a value, is a slot. Of course, there are 6 of them, so I'll say, I'll print 6 hex digits, and I'll put a 0 in there to indicate that any values on the left side of the 6 digits that are 0, it should print zeros. And I will put a new line in there, and then I'm going to print val, and I will mask val with the six digits, the six slots, and that is it. So I will save this, and we'll see if we can compile it. Now, as I mentioned, this should give us, if this runs, this should give us 6 permutations. And it does, 0, 1, 2, 1, 0, 2, 0, 2, 1, 2, 0, 1, 1, 2, 0, 2, 1, 0. And the 3 leading Fs there are the unused slots, because I'm only using 3 of the 6. If I edit the code and I change n to 4, this should give me the 24 permutations that I showed earlier, and there they are. So these match up to the permutations that I had earlier in the lecture. Okay, so the C code is done. Now let's write the assembly code. So for that, I need to download RARS from Moodle. That is a jar file, which I've already downloaded. I've put in my home directory. To run it, you would just type java-jar, and as I mentioned, it's my home directory, and it's called RARS. Okay, so I don't have Java, so I will have to install that. So I'll go ahead and just install default JRE. Password is CSCE 611.
Five hours later.
Okay, so Java is now installed. Let's try running RARS again. And there's RARS. Okay, so now that I have RARS open, let's see. I am going to move this window to the left, and then I will move my terminal to the right. I'll hit Control Z to push RARS into the background, or actually suspend it, and then I'll push it in the background with VG, and then I'm going to open up my permutation.c and set tab stop 4, set tabs, okay. All right, so now I have the C version to the right, and I will have my RISC-V version to the left. So I'll create a new file in here, and the first thing I need to do is basically create these. Well, actually, yeah, I'll create N, and I'll create my defines first. So in the way you do this in assembly would be using the .eqv. So N will be 3 and L will be 3 initially. And then I need my data section where I will basically just put my stack label at the beginning of the data section, and the stack can have the whole data section. I won't allocate anything else. Then I'll start my text section, and then I will have my main function. Okay, so the first thing I need to do is I need to get N and L into registers, and then I'm going to keep these registers set throughout the whole program. So you have to be careful not to step on them to reuse them. So and also I'm going to adopt this practice where I'm going to use comments to basically to show. Oh, can I not copy and paste? Oh, okay. Okay. Copy. Ooh. Okay. Okay. Oh, sorry, I guess I can't copy and paste. Oh, that's no good. Okay, I guess I can't copy and paste from Vim over here to RARS. It's odd. That's okay. Comments in RARS start with the pound, so I am going to basically just use a comment to show what's happening in the assembly code is corresponding to each line of C code. So I'm going to basically define my C. The way I'll do this is I'll do a load immediate instruction, and I'm going to pick a high register number here so I can try to avoid using registers that I may use later. So I'm going to start with X12, and I'm just going to stick N in there, and then preload literal N, and then I'm going to do the same thing for L. So I will load immediate X13 will be my L. So preload literal L. Now again, make sure you don't, I have to make sure I don't reuse X12 and X13, or it'll cause problems. I got to remember that those are live registers. Okay, so next, the stack. I'm going to be doing pushing and popping on the stack. I need the address of the stack somewhere. So I'm going to set up another register. I'll use 14, and I'll load the address of stack into 14. So that way I can always have access to that. And I'm gonna line these up. There we go. We're lined up. Okay. So moving along, I need to initialize top, so I will do that. I will do the same thing. Now in this case, I'm going to use X1 for top. So int top equals 0, so this will be initialize top, and then the next line of code is stack top plus plus equals 0, 0, 1, 2, 3. Okay, so now I'm going to push my initial value onto the stack. How do I do this? Well, first I need the value, so I will do a load immediate with x2, and I'll put my value on there, which is 0, 0, 1, 2, 3, 4, 5, 6. Okay, and now that x2 is just, you know, obviously going to be temporarily used just to hold that value so I can store it. But in order to store it, I need to calculate the address in the stack where I want to store it. I have the base address of stack is going to be in x14, but I have to add the offset. Now, obviously the offset I know at this point in the code is 0, but I'm still going to go through the motions here so I can reuse this code later when I access this, when I pop later, so, or push later rather. So I'm going to do an add. Let's see, I'll use x3, and I'm going to take x14, which is the stack, and I'm going to add x0, which is the, sorry, x1 rather, which is the stack top. And then I'm going to do my store word, and obviously storing x2, which is the initial value, and I'm going to store that to the address that I just calculated in x3. And then I need to increment my stack pointer. Now notice that you know, the stack is words, it's 4 bytes per word, it's a 32-bit machine. So in this case, my stack top is not going to increment by just 1 as I did my C. It's going to increment and decrement by 4 when I push and pop the stack. So I'm going to do an add I, and the stack top is x1, and I will be incrementing that by 4 for the push. So again, I mean, we know that x1 is 0, so the add instruction is a little redundant, but I prefer to do it the way that you would normally do it when pushing, so I can reuse that code later. Okay, so now I'm going to start my outer loop, which is basically a while top. And the first thing that happens inside the loop is I need to see if I'm going to exit the loop. While loops are pre-test loops, so the first thing that you do is test as opposed to a do while, which is a post-test loop. So I'm going to go ahead and check to see if BEQ 0, and I'm looking at x1, if x1 is 0, because x1 is my stack top, and if it is, I'm going to go to exit, basically exit the loop. BEQ 0, by the way, is a pseudo instruction, which evaluates to a BEQ with the register 0. But that's okay, I can use pseudo instructions, especially ones that just evaluate to just one machine instruction, not a big deal. Okay, so the next thing I do is I am going to pop, which is done with this where I say int val equals stack minus minus top. So the first thing I need to do, I'm decrementing top before I use it to index stack, which is why the minus minus comes before top, so I need an add I here, and I'm going to take x1 minus 4. You might say, why not use a sub I? Well, there's no sub I. There's not in MIPS either. I have to add I with negative value. So this was a decrement stack pointer, and then I need to add the x1 to my stack address, which is x14, which is similar to what I did up here when I did the push. And then instead of store, because I'm popping, I'm going to do a load. So I'm going to load into x2 will be my temporary, and x2 of course is the address. So x2 is the address, and then I'm using that address in the load and then immediately replacing it with the value that I loaded. Okay, all right, next line of code is setting found to 0. So this one, again, this is very dangerous because found is a register that will remain live for a long time. So I want to make sure I don't step on this one. This one I'll use x3, that'll be my found. So we'll set that to 0, make sure you don't I'll make sure we don't use that for anything else. The next thing that happens is our for loop. So for int digit equals 0, digit less than L, and then digit plus plus. So, again, these comments are just, so I know, what's going on relative to the C code. Okay, so, for loop. So how are we going to do a for loop? Well, for loop is, first thing that happens is you do the initialization part. So I'm going to need a load immediate for that, obviously. So I need to load a register that will correspond to the digit iterator. And I need to pick a register here. I'll use x4. So I'll set that to 0. And then I'll have my D loop, digit loop, start. So the first thing that happens in there is I need to set my mask up. So int mask equals 0xf, and then shifted left by digit times 4. Okay, so how am I going to do this in assembly language? Well, I need the FF, so load immediate. I guess we'll go x5. I'll load my FF, actually just F, sorry. Right, just F. Just one F, because each digit is only 4 bits, not 8 bits. And then I will shift left logical immediate, and I will I'll go ahead and just put this into x6, and I'll be shifting what I just put into the digit was x4. The F is x5 rather. And then how much am I going to shift that by? Scratch that. Now I've got the F, and I need to multiply the digit by 4 to serve as my shift amount. So in order to multiply by 4, I'm also going to do a shift for that. So I'm going to do an SLLI, shift left logical immediate. Now, one of the things you'll notice, this is a difference from between RISC-V and MIPS. In MIPS, you would just use an SLL instruction. You wouldn't have to use an SLLI instruction. But in RISC, if you have a shift amount that is a constant, you need to use an SLL, shift immediate, essentially. So there's the SLL, SRL, and SRA versions of that. And then if you don't have the I, then you're essentially doing what in MIPS would be a shift variable. So in other words, SLL in MIPS is SLI in RISC-V, and a SLLV in MIPS would be just an SLL in RISC-V. So I'm going to shift, let's see, I need another temp register. I'll use x6. X4 is the digit. That's what I want to shift. That's the loop iterator. And I'm going to shift by 3, which would multiply it by 8. It's 2 to the 3rd power. And then I'm going to finally, I get to shift the mask, which is, let's see, that was put into x5, and I'll just leave it in x5. So I'll shift x5, put it back in x5, and I'll be shifting by the value in x6. Oh, and I'm sorry, not shifting by 3. I'm actually shifting, I'm not shifting by 8, I'm shifting by 4. So that should be 2, actually, 2 raised to the 2nd power, shifting by 4. Keep confusing the slots, keep thinking they're 8 bits when they're 4 bits. Okay, so there we go, and then the next thing we do is we say if val, there's 2 parentheses, if val and mask equals mask. Okay, so then we need to implement this condition. So I'm going to go ahead and just use the AND operator here. I'll use x9 as my temporary here, and x2 is the value that I popped, correct? That was, yes, loaded 2, and then I'm going to AND it against my shifted mask, which is in x5, and then I want to see if branch not equal. I want to see if x9, if it doesn't equal the mask value, which was in x5. Now you might say, wait a second, the if statement checked to see if they were equal. Why are you checking to see if they're not equal? Because this is a very common thing in assembly language. Generally speaking, when you have an if statement, you check for the if statement to be false in the assembly code. So then if it is false, you can skip over the next part, which would be the body of the if statement. So you have to kind of, the conditions are reversed for if statements. So if that's the case, I'm going to skip, right? I'm going to skip the body of the if statement. So if I go through the fall through instruction, then that means that the if is true. And of course, if it is true, I want to set found to 1. And so for that, I just need to do a load immediate. Now I have to figure out what I used for found. Found was x3, right? Yeah, x3. So I'll set that to 1. And then the next thing I'm going to do is start another loop. So for int, let's see, I equals 0, I less than n, and then I plus plus. So I need to start out this new for loop. Now I need to pick what register for my I. Let's see, so we'll load x7, I guess. Yeah, x7 is not used. I'll load that, and then I'll have my my for loop. I'm going to call it v loop, which is my value loop. And then inside here, I want to say, let's put this extra line here. I want to say, let's see, inside here I say if not val and with 1 shifted by 24 plus I, and then 1, 2, 3, 4, 4 parentheses. Let's see, let's do an and I. Add I. I'm going to do an add I. I want to add 24 to, let's see, I'm going to use 8 for my new temporary. X7 is my I value, and then I'm adding that to 24. Okay. And then I'm going to load an immediate here. I need another temporary, so I'll use X9. I'll put a 1 in there, and then I'm going to shift left logical X9. So X9. I'm going to shift X9. I'm going to put the result in X9, and I'm going to shift it by the amount that I just computed in X8. And then I need to do my AND operation. I'll use X10 as another temporary, and I'm ANDing X2, which is my value, my original value. It's been a while since we've used that, but that's the value that I popped. And then I'm going to AND that with X9, which is the thing I just shifted. And then I'm going to say branch not equal 0. I'm looking at 10. And so if it's not equal to 0, that means that there's a 1. That means that, you know, we've already used this value, can't use it. So we're going to have to go to skip 2. Okay, so now the next part here is, let's see, after the if statement, it looks like we can start to, oh, we have to put in the 1 bit, right? So that would be the int new val equals val ORed with 1 shift to the left by 24 plus I, right? That's the next thing to do after the if statement, yes. And then, so for that, I just need an OR, because by taking X2, which is the original val, and I'll OR in X9, which is the bit I've already shifted, and then saving that to X11, X11 then becomes new val. Okay, so that's only one instruction. And then the next thing is I have to say new val equals new val, and then and that with not mask, or the I shifted left by 4 times the digit. Okay, all right, so this one is going to require a few instructions. Let's see. So first thing we need to do is do a not. Not is a pseudo instruction. That's okay. We're going to be notting x5. I'm going to use x8 as a temporary because the last time I used x8 was up here, and that's not using that anymore. And then now we need to do an AND operation. So we will AND, let's see, obviously x8, which is the thing that we just computed, we're going to AND that with x11, which is our new val, and we'll put the result back into x11. So this will clear out the slot, and then after we clear the slot, we need to basically OR in the digit, but before that we need to shift the digit itself. I don't think we've done that yet, actually shifted the digit yet. So we need a shift left logical. I'm just going to use x16. It's probably, don't have to go that far, but and then we're going to shift x, let's see, what is our iterator here? x7, and we're going to shift that by 2. So x16 will actually be the shift amount. We don't have to actually shift. We've already shifted the digit by 4 or by 2 to multiply it by 4, and we have that in x6. So we can just reuse that here. I don't believe we haven't reused x6 yet, so we'll go ahead and use x6 as the shift amount. So we've already got the digit multiplied by 4. It's an x6. x7 is the actual digit that we want to put into the slot, and then we will put that into x16, which is a temporary, and then we can OR x11 with x16 and x11. Okay, next step is we need to push onto the stack. So stack top plus plus equals val. That's our new val rather. That's our push. So we will then add. We'll use x15 as a temporary. x14, which is our. I believe, yeah, x14 is our stack, and we're going to add to that the stack top, which is x1. So this computes the effective address, basically indexes stack with stack top. Then we do a store word with x11, and we're going to put that into the address that we just calculated on x15. And then we're going to do an add I. We're going to add x1 by 4. That's going to increment the stack top. Okay, so now we are done with the if statement. The if statement that we originally were in was one here. If the if statement were false, we went to skip 2. So now this is where we have our skip 2. Okay, now starting with skip 2, so that basically brings us down to here in the C code. We're basically going to end the for loop, so we're going to add 1 to x7, which is this inner for loop, the I loop. So we're going to add I, x7, 1, and then we need to check to see if we're going to do the for loop again. So branch less than, if x7 is less than x12, because if I recall, x12 is where we put in n. Yep, x12. So if we're going to do that again, we're going to go to v loop, which is our value loop. Okay, all right, great. And then, so the next thing we want to do is basically we'll have come out of this loop, and so we're at the break. So we're going to break, which means that we're going to jump out of this for loop, right? Which means that we want to basically go to the next iteration of the while loop. So we will then just jump to loop. Okay, so now we have to begin the next iteration of the digit loop, the D loop. So for that, we need to increment the iterator for that. And I've already forgotten which register I used for that, so let's go up here to the D loop, and I can see it's 4. So I'm going to add 1 to 4, x4, 1, And then we need to check to see if we're going to continue with that loop. And this, of course, we're going to be comparing against L. And L we had an x13. So basically branch less than if x4 is less than x14, right? Because that's L. And we're looking here, we're at L. Sorry, 13, yeah. Sorry. 13, not 14. 14 is the addresses stack. So we're comparing 4 to 13. And if it's less than, we're going to go back to the beginning of the D loop. And then, so now we're down here. We're finished with the D loop, which is this for loop. Now we're down to the if statement. So we need to see if, let's see, we're going to check to see if not found, printf, dot, dot, dot. And so, again, we're going to check the converse of that. So branch if not equal to 0. We're looking at found, which is x3, I believe. Yes, if x3 is not equal to 0, then we skip. So we're going to go to, we need another skip label. Actually, I'm just going to go back to loop. I'm going to just go back to the top of the while loop. Okay, and then because there's nothing under this line in the while loop. And so now we need to print. So how do we print? Well, there's these E calls, system calls. This is equivalent to syscall in MIPS. You might remember that from 2.12. But if you go to help under RARs, and you can see that the syscalls are listed here. In our case, we want to print a hex number. And it looks like we've got the ability to do that. Print int hex is number 34, and it tells you up here on how to actually scroll up here. It tells you how to do it here. So pretty much use A7 to denote which one you want. In this case, 34, and then A0 is what you want to actually send in as the argument. So again, A7 and A0. Now we need to make sure that we're not already using A7 is register 17. I don't believe we use that one. So I am going to, we want to do a load immediate A7. We're going to put 34 in there. That tells it to print. And then we need to copy the value that we want to print, which of course is going to be our value, the original value that we popped, which is in x2, right? So we need to copy x2 to the parameter, but we want to do the and first. So I'm going to do a load immediate in x15, and I'll go ahead and put in the mask value 1, 2, 3, 4, 5, 6. And then we will do our AND operation, and I will just put it directly into A0. That would be x15 and x2. And then I will do a load immediate, and I'll put sorry, I already did A7. Yes. And then I just do eCall, and then the problem now is that this will print the hex value, but it won't print a new line character, unfortunately. So we have to do a separate eCall for that. So if we go back to help and we look at syscalls, we need to print a character. Yeah, print a character is number 11. So once again, we do a load immediate on A7. I'll put 11, and then we can load immediate into A0 and put in a new line character, and then basically eCall that. So that should print a new line character, and then of course we're done with the body of the while loop. So we just go back to loop, and then I believe if the while loop ends, we go to exit, right? So then we can exit. And that's it. So I will save that, and we will just save it as the default, actually I'll call it permutation.asm. And first thing you want to do is assemble it. You hit the assemble button here. It looks like we already got an error. Symbol skip is not found in the symbol table. So we had a skip over here. It looks like we forgot to define that. So basically, if this if statement were false, then we need to, this, by the way, this if statement is if val and mask, that's this guy. So if that were false, we'd want to essentially go down to basically the end of that for loop, right? Which is when we would be adding a 1 to digit, and digit was the D loop, so that's x4. So wherever we incremented x4 by 1, right? Which would have happened all the way down here. So we'll put our skip label down there. Yeah, so that's the end of the digit loop. All right, let's save that and reassemble it, and it looks good. And then we'll go ahead and we'll run it, and it looks like it printed one value, 012. Let's reset that and rerun it. Ah, there we go. Now we have all the values, and there's all 6 of them there. Did that match what we got with the C code? So we got 102. That was the second value you got in the C code. 021. 201, 120, 210, and 012. So for some reason, this, the 102 was first in the C code, and oh, I see. It was, we got the the 012 was first in the C code, and it was printed last in the assembly code. I'm not sure that shouldn't have happened, because the assembly code is doing exactly the same thing the C code is doing. That might indicate that there's a buffering issue with the syscall versus the printf. But as far as I could tell, the assembly code's working the same way. So that is it's an example of building out a fairly complex program in RISC-V assembly with lots of nested loops and bit manipulation. Now that we've introduced System Verilog, we're ready to start designing a large-scale digital logic design. What should we design? Well, a CPU, of course. In previous instances of this course, we designed a MIPS CPU because this is the architecture with which you are familiar from CSCE 212.